Welcome to the Deep Dive. We take a stack of sources, pull out the key insights, and give you the knowledge you need fast. Today we're getting into something really quite profound and often misunderstood from World War II, the Japanese kamikaze attacks. Our main source is a pretty comprehensive Wikipedia article, which lets us look at this from, well, a lot of different angles. We want to go beyond that simple image, of just suicidal pilots. This was a really complex thing born out of sheer desperation and a very unique cultural background. So our mission today, define it, trace its origin, see how it became like an actual strategy, look at the impact, and importantly, the human stories.
Exactly. This isn't just about military tactics. It's an exploration into what really motivated these actions and how they fundamentally changed naval warfare in the Pacific. We'll be looking at strategy, yes, but also the human side. And honestly, there are some surprising facts and different viewpoints in the sources that might challenge what you think you know.
Okay, let's start with the word itself, kamikaze. Most people know it translates as divine wind or maybe spirit wind, right?
Right.
But here's where it gets really interesting. The term isn't from World War II originally. Its roots go way back, centuries actually, to these two massive typhoons, 1274 and 1281. They basically wiped out Kublai Khan's Mongol fleets when they tried to invade Japan, seen as, well, divine intervention saving the country, hence divine wind.
Yeah, and the linguistic side is fascinating too. While we all say kamikaze, the formal Japanese term during the war was Shinpu Tokubetsu Kukikitai, which means Divine Wind Special Attack Unit, often just shortened to Kukitai, Special Attack Unit. Now, Shinpu and kamikaze use the exact same Japanese characters. Shinpu is the more formal reading, the on reading. Kamikaze was originally the informal kun reading. It wasn't really used officially for these suicide attacks during the war, but it's the term that caught on globally afterwards.
Right, and now we use it generically for any kind of self-destructing weapon, even like kamikaze drones today. Amazing how a 13th century term sticks around. Okay, so before these became official units, pilots sometimes deliberately crashed their planes anyway. What was going on there, these early Tayatari or body attacks?
Well, these were mostly last-ditch efforts. A pilot's plane is heavily damaged, maybe going down anyway. So the thinking was either avoid being captured, which was seen as a dishonor, or try to do maximum damage on the way out. We saw examples early on. Lieutenant Fusada Ida at Pearl Harbor, December 41. His plane was hit. Seems he deliberately crashed it. Or remember that damaged American bomber at Midway? Flew right at the Akagi's bridge. And maybe one of the most impactful early ones, a Japanese Betty bomber crashing into the USS San Francisco at Guadalcanal. Huge impact on that battle.
So these individual acts are happening. What's the bigger picture for Japan? How bad was their situation by then?
Pretty dire, actually. Battles like Midway, the Solomons Campaign, they inflicted, well, irreparable damage on the Imperial Japanese Navy Air Service, the IJNAS.
They just couldn't replace the losses, right?
Yep.
Not the carriers, not the experienced pilots.
Exactly. Their whole initial plan banked on a quick war. They had no real long-term plan for replacing ships, pilots, sailors. The losses were mounting, and they couldn't keep up.
And the U.S. technology and training was improving dramatically, too.
Massively. By 1943-44, you have the U.S. bringing in newer, better planes like the Hellcat, the Corsair. Plus, American pilots were getting better training and more combat experience. This really came to a head in the Battle of the Philippine Sea, June 44. The Americans called it the Great Marianas Turkey Shoot.
Oof.
Yeah. Japan lost over 400 carrier aircraft. Their carrier air power was basically wiped out.
And then Saipan falls in July 44. That must have been a huge blow.
Strategically, it was devastating for Japan. It gave the U.S. forward bases for the B-29s to bomb the home islands directly. And it clearly signaled the Allies were pushing towards the Philippines.
Which was vital for Japan's oil, right? From Southeast Asia.
Absolutely critical. So their air power is gone, their supply lines are threatened, options are running out fast.
Okay, so that sets the stage. Desperation mounting. How does this idea, the kamikaze attack, become an official organized strategy?
Well, the name often credited with first officially proposing it is Captain Lotoharu Okamura. This was around June 1944. He apparently referred to volunteers as a swarm of bees. Bees die after they sting. He genuinely believed crash diving was the only way left.
But the real turning point, the moment it became official policy, seems to be that meeting on October 19th, 1944, Mabalacat Airfield.
That's the one. Vice Admiral Takijujishi shows up. The light Gulf invasion is imminent. He's got, maybe 41 planes operational. an impossible situation.
And he makes this incredibly stark decision.
Yeah. His statement to his officers was brutally clear. He basically said, look, I don't think there's any other way to hold the Philippines than to put a 250-kilogram bomb on a Zero and let it crash into a U.S. carrier, disable her for a week. That was the goal, a desperate gamble.
So how did they form that first unit?
Commander Aseiichi Tamai, he gathered 23 student pilots he'd trained. He asked for volunteers. The sources say every single one raised both hands.
Wow.
Then Tamai asked Lieutenant Yukio Seki, a very promising pilot, to lead them.
How did Seki react? This sounds incredibly heavy.
It's really poignant. He apparently closed his eyes, thought for maybe 10 seconds, then accepted. But later, he reportedly said, Japan's future is bleak if it is forced to kill one of its best pilots. And even more tellingly, I am not going on this mission for the Emperor or for the Empire. I am going because I was ordered to.
Wow, that completely challenges the whole eager volunteer narrative, doesn't it?
Yeah.
Raises serious questions about how voluntary it really was.
It absolutely does. It shows the immense pressure, even on those who seemingly volunteered. A very different picture than the propaganda.
Still, they formed the unit, gave the subunits these poetic names, Shikishima, Yamato, Asahi, Yamazakura.
Yeah, from that classical poem about cherry blossoms. The spirit of Japan, Shinichi told them their nobility of spirit would save the homeland. Heavy symbolism.
So the Lake Gulf invasion kicks off, and these attacks begin in earnest.
Right. Though there's a bit of debate about the very first one. HMAS Australia got hit October 21st.
Was that a planned kamikaze mission?
Possibly deliberate, but probably not from the official, newly formed Special Attack Force.
Right.
And USS Sonoma, a tug, was sunk on the 24th, also before Seki's unit flew.
Okay, so the first official mission, led by Lieutenant Seki, was October 25th, 1944, during the Battle of Leyte Gulf.
Correct. Seki's unit went after U.S. escort carriers. He initially aimed for USS White Plains, but there was heavy anti-aircraft fire, so he aborted that run, banked, and dived straight into USS St. Lo.
And the impact.
Devastating. His bomb exploded on the flight deck, caused massive fires. Eventually, the ship's bomb magazine detonated and the St. Lo sank.
A major success for them right from the start.
Huge. It wasn't just sinking a carrier, it sent a shockwave through the Allied forces. Suddenly, they're facing pilots used as guided missiles. It forced a total rethink of defenses.
And the hits kept coming immediately after.
Oh, yeah. By October 26th, the next day, 7 carriers had been hit. Sangamon, Santee, Suwannee, White Plains, Callanan Bay, Kitkin Bay.
Plus other ships.
Yeah, over 40 other ships damaged or sunk in just those first couple of days.
That initial success must have fueled the whole program.
Absolutely. It seemed to validate this incredibly desperate tactic. The program expanded immediately, massively. Over the next few months, you see something like 2,000 aircraft making these attacks.
Did they try using them against the B-29s that were bombing Japan?
They did. They formed special units like the Shinten Special Unit specifically for that. But it was much less successful. B-29s flew high, they were faster, surprisingly maneuverable for their size, smaller targets than ships, and bristling with defensive guns. Much harder to hit.
And they started developing planes specifically for kamikaze missions, too, not just modifying existing ones.
Right. That shows the strategic commitment, grim as it was. You had the Yokosuka MXY-7 Oka, basically a rocket-powered, human-guided bomb.
The Americans called them baka bombs, right? Idiot bombs.
They did, derisively. Then there was the Nakajima Ki-115 Tsurugi. Super simple design, easy to build quickly from non-strategic materials, even wood. Even had landing gear you could jettison after takeoff so it could be reused on another plane. Designed purely for one-way trips.
It really shows how far down the road they were. Pouring resources into weapons designed only for self-destruction.
Yeah, it wasn't about winning anymore, maybe just about making the Allied victory as costly as possible.
So the Allies are facing this horrific new threat. How did they adapt? How do you defend against something like that?
Well, a key figure was Commander John Thack, already famous for air tactics like the Thack Weave. In early 45, he developed this defensive strategy called the Big Blue Blanket, multi-layered defense.
What did that involve?
Bigger combat air patrols pushed out much further from the carriers, like way out, establishing a line of picket destroyers maybe 50 miles, 80 kilometers out, loaded with radar for early warning, better coordination between the ships and the fighter patrols, and just keeping fighters up constantly around the clock.
And they went on the offensive too, didn't they? Hitting Japanese airfields.
Yes, very aggressively. Intensive fighter sweeps over Japanese airfields to catch planes on the ground.
Yeah.
And bombing runways with delayed action bombs. Made repairs really difficult, kept planes grounded.
And the Allied pilots and planes were just better by this point.
Generally, yes. Allied pilots had more experience, superior aircraft like the Hellcat, the Corsair. The British Pacific Fleet had their Seafires, too. These often poorly trained kamikaze pilots, sometimes rushed through training, were frankly easier targets for skilled Allied fighter pilots. I mean, the U.S. Fast Carrier Task Force alone could put over 1,000 fighters in the air. It was an overwhelming advantage.
Did anti-aircraft fire get better too? Ship defenses?
Definitely. There was a big shift towards heavier guns. The 5-inch .38 caliber became crucial. It had the power to actually destroy an incoming plane at a safer distance. Because just damaging a kamikaze wasn't always enough, it could still keep coming. And the introduction of the VT fuse, the proximity fuse, made AA fire much, much more effective. Shells would detonate near the plane, not needing a direct hit.
So where did the kamikaze attacks really reach their peak intensity?
That would undoubtedly be the Battle of Okinawa, April to June 1945. They came in huge coordinated waves. The Japanese called it Operation Kikusui, floating chrysanthemums.
What was the toll at Okinawa?
It was brutal. Japan used about 1,465 aircraft in kamikaze attacks there. They sank or put out of action at least 30 U.S. warships, mostly destroyers and smaller ships, especially those on that dangerous picket duty out front. Some Allied merchant ships, too.
But no big carriers or battleships sunk.
No, none were actually sunk by kamikazes at Okinawa, despite the ferocity of the attacks. Damaged, yes, some heavily, but not sunk.
Isn't that where the story of the USS Laffey comes from? The ship that would not die?
That's the one. An incredible story. Survived 6 kamikaze hits and 4 bomb hits in one engagement. Just kept fighting. Legendary resilience.
There was a noticeable difference in how U.S. and British carriers handled the hits, wasn't there? Something about the deck construction.
A really significant difference. American carriers mostly had wooden flight decks. They tended to suffer, well, much more catastrophic damage and higher casualties when hit. USS Bunker Hill, for example, hit by 2 kamikazes in quick succession. 389 men killed or missing. Devastating.
And the British carriers?
They had armored flight decks, so when they got hit, and they did, 5 British carriers took 8 kamikaze hits. The damage was usually contained topside. Total deaths across all those hits on British carriers, only 20.
Well, that's a stark contrast.
It really was. And the Brits could repair damage incredibly quickly. HMS Formidable got hit, fire on the flight deck, but she was launching planes again within hours. It led to that famous, maybe slightly exaggerated, quote from a U.S. liaison officer. When a kamikaze hits a U.S. carrier, it means 6 months of repair at Pearl. When a kamikaze hits a limey carrier, it's just a case of sweepers, man your brooms.
Shows the design trade-offs, I guess. So were these attacks always single-engine fighters?
Mostly, but not always. They did use some twin-engine bombers occasionally, carrying larger payloads.
And the very last ship sunk by kamikaze attack in the war.
That was the destroyer USS Callahan, July 29, 1945, hit by an obsolete biplane, believe it or not. Wooden frame, fabric covering, shows how desperate they were for anything that could fly.
Were there attacks after the main Pacific fighting, like against the Soviets?
Yes, though they're much less known. During the brief Soviet-Japanese War in August 45, there were attempts, like Lieutenant Tsuyohara trying to ram a tanker in Vladivostok, and Admiral Ugaki leading a final unauthorized strike after the surrender announcement.
Were they effective?
Largely ineffective by that point, but what's really mind-boggling is the sheer number of planes Japan still had ready at the time of surrender. Over 9,000 aircraft total. And get this, over 5,000 of them were apparently fitted out, ready for suicide missions, anticipating the Allied invasion of Japan itself.
An unimaginable scale of planned sacrifice. So let's try to sum up the effectiveness. Did the strategy work, in a sense?
It's complicated. They caused immense damage and heavy casualties, especially to U.S. carriers in 45, no doubt about that. But as we said, they didn't manage to sink any fleet carriers, cruisers, or battleships outright with kamikazes alone.
But damaging ships like Franklin, Bunker Hill, Enterprise so badly they were out for the rest of the war. That's almost as good as sinking them, operationally speaking.
From the Japanese perspective, yes. Taking those vital assets off the board, along with their experienced air groups, was a significant achievement, even if temporary. It definitely hurt the U.S. Navy's operational capability at a critical time.
You mentioned Admiral Spruance. His assessment sounds pretty stark. A very effective weapon, which we must not underestimate. He'd seen it firsthand.
He had. His flagships got hit twice. He knew the threat was real. Statistically, the numbers vary a bit depending on how you count, but the U.S. Air Force figure suggests around 2,800 kamikaze attackers sank 34 Navy ships, damaged 368 others, killed about 4,900 sailors, wounded over 4,800. Bill Gordon's research lists 47 ships sunk, including escort carriers and destroyers. Whatever the exact number, the human cost was horrific.
Which brings us to the pilots themselves. The human cost, and that really difficult question of recruitment. Was it truly all volunteers?
The official Japanese propaganda absolutely pushed that narrative, a swarm of bees eager to die for the emperor. But when you look at uncensored letters, diaries, you see something much more complex, a whole myriad of emotions, as one source puts it. Yes, there's determination, protecting the homeland, gratitude to families, but also immense sorrow, lost loves, and just the crushing weight of knowing you're about to die. Not simple zealotry.
And some accounts paint an even darker picture, right? Like that quote from Sunio Watanabe.
Yeah, the former editor of the Yomiuri Shimbun, a very harsh assessment. He called them sheep at a slaughterhouse and claimed some pilots were physically unable to stand, had to be carried and pushed into their planes.
That's horrifying. It really forces you to question the line between patriotism and outright coercion.
Absolutely. How much real choice did they have? And the training methods seem to back this up. Accounts describe incredibly harsh physical training, constant corporal punishment, brutal beatings. Takeo Kasuga called it cruel and torturous, a daily routine. Daikichi Irakawa recalled being beaten so badly his face was unrecognizable.
He said it eliminated patriotism for many pilots.
That's what he believed. Replaced it with a kind of resigned acceptance, just broken down.
And the rituals before the mission. The manual telling them to eliminate thoughts of life and death, shout Hisatsu at impact.
Yes, all part of the process. Ceremonial sake, the senninbari belts sewn by women, writing death poems, even being issued pistols to commit suicide if captured.
The pressure must have been unbelievable. That story about the pilot shot after returning 9 times due to mechanical issues.
If true, it's chilling. It speaks to the absolute expectation of fulfilling the mission no matter what.
So it's this incredible complex mix of factors, isn't it? Cultural indoctrination is a big part.
Definitely. State Shinto, the imperial rescript on education, decades of reinforcing the idea that dying for the emperor in Japan was the ultimate honor. Enshrinement at Yasukuni Shrine was part of that.
But maybe simpler, more human motivations too, like
Yeah.
protecting their families.
Yes, fear of what might happen to their families if the Allies invaded, fueled by propaganda about Allied atrocities. That's a powerful motivator. And we shouldn't forget the stigma faced by pilots who survived. Returned from a mission due to malfunction, or got shot down and rescued. That took decades to fade.
It wasn't universally supported within the military either, was it? Some high-profile figures were critical.
That's right. People like Minoru Genda, who planned Pearl Harbor, and the famous ace Saburo Sakai. They thought it was a waste. Skilled pilots should be shooting down enemy planes, not turning themselves into bombs, a misuse of valuable assets.
So wrapping this up, this deep dive into the kamikaze, it really shows, well, a complex storm of strategy, culture, desperation, and intense personal sacrifice.
Absolutely. Connecting it to the bigger picture, it's a stark reminder of the brutal realities of total war, the extreme lengths nations will go to when they feel cornered, and it really makes you think about how history remembers and portrays these kinds of actions, often simplifying them way too much.
Yeah, the story isn't just about the planes crashing. It's about the individuals inside them, the immense societal pressures. It forces you to look beyond easy answers, understand the context. So for you, our listener, maybe something to think about is this. How does our understanding of sacrifice in war change? When the goal shifts from, fighting potentially to the death to fighting with the absolute intent of death, what does that reveal about human limits, devotion, maybe even desperation?
Imagine, just for a second, a camera so incredibly powerful it maps the entire visible southern sky, not once, but every few nights, uncovering the universe's biggest mysteries, like almost in real time. Well, this isn't science fiction anymore. It's the Vera Rubin Observatory, and get this, it just released its first truly stunning images. So, welcome to our deep dive into this astronomical marvel, because this isn't just another telescope, is it? It's revolutionary, poised to create the most comprehensive, dynamic map of our universe ever conceived. Now, you've shared some amazing sources with us, a really deep Wikipedia dive, for instance. And our mission today is to, cut through all that dense information, pull out those absolutely vital nuggets of knowledge, and give you a shortcut, really, to understanding why this observatory is such a massive game changer. We'll unpack its kind of surprising history, its unique design, and what it means for understanding things like dark matter, cosmic explosions, even those potentially dangerous asteroids near Earth. So, just starting off, what really jumps out to you about a project this ambitious? Okay, let's start unpacking this beast, because before we even get to the incredible tech, the name itself has a story, doesn't it? It wasn't always the Vera Rubin Observatory.
No, that's right. Originally, it was known as the Large Synoptic Survey Telescope, LSST for short. And that word synoptic is from Greek. It means something like together view or a broad overview, which honestly perfectly captures the core mission, right? Surveying the whole available southern sky repeatedly, giving us this wide view of how things are changing over time.
Right. And the renaming, that's such a fantastic tribute. It became U.S. law, late 2019, announced in 2020, honoring Vera Rubin, an amazing American astronomer. Her work on how galaxies rotate, that was some of the strongest early proof for dark matter, so it really connects the observatory's mission right back to her legacy.
It absolutely does. And what's kind of neat now is how the names sort of clarify the different parts. So Vera Rubin Observatory, that's the whole facility, the buildings, everything. But the actual telescope inside, that's the Simony Survey Telescope, named after Charles and Lisa Simony, who were major private donors early on, and LSST. Well, they cleverly repurposed that acronym. It now specifically means the Legacy Survey of Space and Time. That's the actual 10-year survey it's doing.
Ah, okay. So this Rubin Observatory, it didn't just appear out of nowhere then. It sounds like it's really standing on the shoulders of giants, part of a long tradition of sky surveys.
Oh, absolutely. You can trace a line, really, from, Messier drawing his catalogs way back when, to those huge photographic plate collections, like Harvard starting in the 1880s. Then the early digital surveys, like Sloan Digital Sky Survey, SDSS. Rubin is definitely the next massive leap in that quest to map everything. And his roots go back further than you might think. There was this dark matter telescope idea floating around as early as 1996. Then it got a formal thumbs up in the 2001 Astrophysics Decadal Survey. And even back then, they had the basic idea sketched out. A 6.5-meter class telescope surveying the sky every week, going much fainter than before.
Wow, 1996, that's a long time brewing. And it got some pretty crucial early private money too, didn't it?
It did, yeah. That was vital. You had Charles and Lisa Simony chipping in $20 million and Bill Gates adding $10 million back in 2008. Now, though, it's more complex. It's funded by multiple agencies. The U.S. National Science Foundation, the NSF is the big one, and the U.S. Department of Energy, the DOE. They specifically fund the camera part because it's so key for understanding dark energy. Plus, there's still private money coming in through the LSST Discovery Alliance. All told, the construction cost was around $680 million.
Okay. And digging actually started, August 1st, 2014?
Well,
with a boost from Congress later on in 2018, which helped speed things up a bit. Building something on this scale, it just sounds like an epic undertaking. Choosing the site, crafting those gigantic mirrors, every single step must have been a huge challenge. So how did they actually, put this colossal machine together?
Well, it really started with finding the perfect spot, Cerpachon in Chile, chosen way back in May 2006. Why there? Well, incredibly clear nights consistently, excellent astronomical seeing, that's how steady the atmosphere is. Plus, there was already infrastructure nearby. And crucially, fiber optic links. You need serious bandwidth for the 30 terabytes of data every night. So they started digging the site in March 2011. And the mirrors, oh boy, that's a saga in itself. The main one, the primary, and the third mirror, the tertiary, they're actually made from one single piece of glass, a monolith. Casting started in 2007, finished casting March 2008, declared perfect later that year, but polishing. That took until 2015. This monolith design, it makes it incredibly stiff, so when the telescope moves, it settles down almost instantly. Super important for sharp images. It finally got to the mountaintop in 2019 and got its reflective coating just last year, April 2024. The secondary mirror had its own long journey too. Years of grinding, shipping, coating. It arrived on site in late 2018. Just monumental engineering feats, really.
Sounds incredibly intricate, like a dance of precision engineering and, frankly, a lot of patience. So the building itself finished in 2018, the dome rotated for the first time in 2019, and that huge telescope mount assembly, the TMA, that holds it all. That was declared basically done just last year, April 2023.
Exactly. And then, of course, there's the heart of it, the LSST camera, which is just a marvel. The DOE greenlit its construction back in 2015. Its focal plane, that's the bit that actually captures the light, is this huge mosaic of 189 individual CCD detectors. That part was finished and being tested by September 2020. The whole camera was reported finished early 2024, shipped to Chile May 2024, and finally installed March 2025. It's been a long haul for all these pieces.
Wow. So after all that incredible work, all those years, that moment of first light, seeing the first images, that must have just been electric. What did they actually see first?
Oh, it was absolutely exhilarating. I mean, they had an initial engineering camera taking some test shots back in October 2024. But the official system first, light images, combining the full telescope and that amazing camera, those were just released June 23rd, 2025, like barely a month ago.
Oh.
The first glimpses they shared were stunning, a beautiful composite image of the Trefid and Lagoon nebulae, and these incredibly wide views of the Virgo cluster of galaxies. And the impact was immediate. Right away, those first images revealed over 2,000 new asteroids. Just like that. You could feel the excitement globally. There were launch parties in, 28 countries? 6 continents? Celebrating the release?
2,000 new asteroids instantly. That's amazing. Truly global buzz. So the full survey, the main science operations, that starts later in 2025. A little bit delayed by COVID, but basically right around the corner. And I love the commitment to open science, making all the data public after just 2 years.
Yeah, it's a massive undertaking. And the scale of this 10-year LSST survey, it's hard to wrap your head around. They expect to catalog over 5 million asteroids. Think about that, including maybe 100,000 near-Earth objects. And beyond our solar system, we're talking about imaging roughly 20 billion galaxies and 17 billion stars, plus like 6 million smaller solar system bodies. The sheer numbers are just staggering.
So, okay, beyond just being huge, what really makes this observatory so revolutionary? How is it going to fundamentally change how we see the universe?
Well, it's this unique blend of power and scope. First off, the field of view is incredibly wide, 3.5 degrees across. That's 9.6 square degrees of sky in one shot.
Yeah.
For perspective, the sun or the full moon, they're only about half a degree wide. So this huge field, combined with its big primary mirror, gives it a massive E10. You can think of E10 as like the telescope's data gathering power.
Yeah.
How much light it collects over how much sky at once. Rubin's E2 is more than 3 times bigger than the next best surveyed telescopes out there, which makes it insanely efficient at scanning the sky.
So it's not just powerful, it's incredibly efficient at grabbing data. How does it manage such sharp images across that enormous view, though?
That's down to a really clever optical design. It's a 3-mirror anastigmat. Basically, this setup corrects for various optical distortions, giving super sharp images across that whole wide field. The primary mirror is 8.4 meters. Huge. The secondary is 3.4 meters, actually the biggest convex mirror in any operating telescope, for now anyway, until the extremely large telescope comes online. And the tertiary mirror is 5.0 meters. And remember that M1, M3 monolith design? That single piece of glass. That stiffness is key for pointing quickly and getting sharp focus fast.
And the lenses. I heard one is like the biggest lens ever made.
That's right. There are 3 big corrector lenses in the system to fine-tune the image quality. And the first one, it's 1.55 meters across, absolutely the largest lens ever built for astronomy. The third lens actually doubles as the vacuum window right in front of the camera sensor. One kind of interesting technical point, unlike a lot of big telescopes, Rubin doesn't actively correct for atmospheric dispersion, how the atmosphere splits colors slightly. That's because it moves so fast. And the design choices mean that for some observations, especially in bluer light far from the zenith, the image quality might be just a tiny bit reduced. But it's a trade-off for speed and survey power.
Okay, and with it moving so much, how does it keep everything perfectly aligned and focused?
It uses something called active optics. Think of it like the telescope constantly checking its own prescription. There are these tiny sensors, wavefront sensors, at the corners of the camera. They measure subtle distortions in the incoming light waves, and that information is used to make tiny real-time adjustments to the shape and position of the mirrors. This keeps the focus perfect even as the telescope slews across the sky. It's different from adaptive optics, which tries to cancel out atmospheric twinkling. Active optics make sure the telescope itself is perfectly tuned.
Right, and then the camera. We touched on it, but it really sounds like the centerpiece.
It truly is, the LSST camera, 3.2 gigapixels. It takes these deep 30-second exposures. And yes, it's the largest digital camera ever constructed, full stop. The focal plane, where the light hits, is 64 centimeters across.
It's this enormous mosaic of 189 individual CCD detectors, each one 16 megapixels. And to keep the electronic noise way down, they have to cool the whole thing to about minus 100 degrees Celsius. It also has a set of 6 different filters, degrizzy they call them, covering light from the near ultraviolet all the way to the near infrared. Though interestingly, the filter changer can only hold 5 at a time, so each day they have to decide which one to leave out.
Okay, so you've got this beast of a camera taking these absolutely massive images every 30 seconds or so. Thinking about that scale, I mean, how on earth do you even begin to manage that flood of data?
Yeah, that's arguably the single biggest technical hurdle of the whole project. We're talking over 200,000 pictures a year. That's 1.28 petabytes of raw data annually. Just imagine, managing it, analyzing it, it needs unbelievable computing power. The initial estimates were like 100 teraflops of processing and 15 petabytes of storage. But those numbers have just kept climbing. Now it's more like 250 teraflops and 100 petabytes.
100 petabytes. That's just mind-boggling. And it gets processed on different timescales, doesn't it? What happens right away?
Exactly. 3 main timescales. First is the prompt data. This delivers alerts within 60 seconds of an observation finishing. These alerts flag anything that's changed brightness or moved compared to older images of the same spot. Just transferring, processing, comparing these huge images in under a minute. It's a massive feat of engineering. But it means we can catch super short-lived events, like maybe the first moments of a supernova as they happen.
And this is where that really fascinating classified processing detail comes in, right?
That's right. It's quite unusual for an astronomical facility. That very first stage of processing, the 60-second alert generation, it actually happens at a secure U.S. government facility. The idea is to scan for any transient events that might inadvertently reveal sensitive government assets in orbit. If something like that is detected, it's temporarily edited out of the public alert stream. Then, after 3 days, when the information is considered less sensitive from a timing perspective, the unredacted data is released. It's a unique setup.
Definitely unique. So millions of alerts per night, potentially, hitting the network almost instantly?
Yep. Up to 10 million alerts are expected each night. And these are fed out immediately to the scientific community through specialized systems called event brokers. These brokers then filter and forward alerts to scientists around the world based on their specific interests. Actually, the Zwicky Transient Facility, or ZTF, another survey telescope, was a key testbed for developing this whole rapid alert pipeline for Rubin.
Okay, so that's the immediate, the real-time stuff. What about the rest of the data?
Right, so the next level is daily products, released within 24 hours. This includes the actual processed images from the previous night, also catalogs of all the sources detected in those different images, the things that changed, and, importantly, initial orbital calculations for any newly discovered solar system objects. Then, the third timescale is the annual release. Once a year. This is a huge deal. They reprocess all the science data gathered up to that point, from the very beginning. This annual release contains the fully calibrated images, super precise measurements of positions, brightnesses, shapes for everything detected, information on how objects vary over time, like curves, and these enormous catalogs. We're talking roughly 6 million solar system objects identified, and something like 37 billion with a B other sky objects. That's 20 billion galaxies and 17 billion stars. And for each of those billions of objects, there are over 200 different measured attributes. The scale is just immense.
Almost impossible to comprehend, really. 37 billion objects, 200 attributes each. But it's not just about the data the observatory pushes out to scientists, is there? There's something about users running their own analysis.
Yes, and this is really innovative. It's called user-generated data products. Basically, the Rubin Data Center reserves 10% of its computing power and disk space specifically for the science community. So instead of you having to download potentially petabytes of data to your home institution, which is often impossible, you can actually write your own custom analysis code and run it directly on the data stored at the Rubin facility. It's a huge enabler. Makes the data so much more accessible for complex custom science questions.
That's incredibly smart. And it's all built on open source software too, right? The pipelines are on GitHub.
That's right. The entire LSST software stack is open source, which is fantastic for transparency, collaboration, and letting others build on it. And just getting the data from the telescope down the mountain and across the world is another challenge. It goes from the summit to a base facility in Chile, then primarily to the U.S. data facility at SLEC in California. This needs incredibly fast network links, 100 gigabits per second, or even faster and super reliable ones. It involves multiple fiber optic cables crossing international borders. It's this amazing collaboration between different networking groups in Chile, the U.S., and elsewhere.
Okay, so we have this unbelievable machine generating this unprecedented torrent of data. What are the really big questions, the grand challenges that Rubin is designed to tackle? What are we actually going to learn?
The science goals are truly profound. A huge focus is on cosmology, understanding dark energy and dark matter. Rubin will do this by making incredibly precise measurements of things like weak gravitational lensing, how massive structures bend light. Also, mapping the large-scale structure of the universe using baryon acoustic oscillations, and finding and studying thousands upon thousands of Type Ia supernovae, which are crucial standard candles for measuring cosmic distances and expansion. Another major goal is mapping our own solar system in unparalleled detail. It's expected to increase the number of known asteroids and other small bodies by like 10 to 100 times. This includes finding potentially hazardous near-Earth objects, NEOs, and exploring the outer solar system looking for Kuiper belt objects. And yes, it will definitely help in the ongoing hunt for the hypothesized Planet 9 if it's out there.
And you mentioned catching transient events, those fleeting cosmic happenings.
Absolutely, that's a huge part of it. The universe isn't static, it's dynamic. Rubin's rapid cadence and alert system are perfect for catching things that change quickly. Think novas, different types of supernovae, the afterglows of gamma-ray bursts, flickering quasars, even rare gravitational lensing events where a foreground object magnifies a background one. The alerts allow other telescopes, maybe ones that can take spectra or observe in different wavelengths, to quickly follow up. And of course, it will create the most detailed map ever of our own Milky Way galaxy, watching how stars move and change. But honestly, one of the most exciting things is the potential for completely unexpected discoveries. Serendipity. When you gather this much data covering so much sky, so deeply and so often, you're bound to find things you weren't even looking for, entirely new phenomena.
That potential for serendipity is always exciting in astronomy. You mentioned EOs, the near-Earth objects. Does Rubin's work tie into specific goals from agencies like NASA?
Yes, very directly. NASA has had a congressional mandate for years to find 90% of all NEOs that are 140 meters across or larger, big enough to cause significant regional damage. The Rubin Observatory, just through its planned 10-year survey, is estimated to found something like 62% of those objects all by itself. And studies have shown that extending the survey by just 2 extra years to 12 years total would likely be the single most cost-effective way to reach that 90% target. So it plays an absolutely critical role in planetary defense, helping us identify potential threats. Beyond the core science, there's also a really strong education and public outreach, or EPO, component. They have partnerships with platforms like Zooniverse for citizen science projects, letting anyone contribute to discovery, really aiming to engage the public, educators, students directly with this amazing facility and its data.
That's great to hear. So stepping back a bit, how does Rubin really stack up against other big sky surveys from the past or even running now? It feels like it's in a class of its own.
It really is unique because it combines several key strengths to an unprecedented degree. The huge field of view, the depth it reaches, and the rapid cadence of its survey, seeing the same sky over and over quickly. If you look back, the old photographic surveys, like the Harvard plates digitized as star glass, invaluable historical record, absolutely. But photographic, much shallower. Even the groundbreaking Sloan Digital Sky Survey, SDSS, which mapped a huge chunk of the northern sky digitally in the 2000s, Rubin goes significantly deeper and surveys much faster.
Okay, what about more contemporary surveys? Pan-STARRS, Gaia, ZTF.
Right, good comparisons. Pan-STARRS in Hawaii, with its 2 telescopes, has been the reigning champ for finding NEOs until now. Its sky coverage area is similar to Rubin's plan, but Rubin's individual images go deeper, see fainter things. The DESI legacy surveys use several telescopes to map distant galaxies over a large area, reaching similar depths, but they specifically avoided the crowded plane of the Milky Way, which Rubin will map intensely. Gaia, the space mission, is incredible for measuring star positions and motions with mind-blowing precision for billions of stars. But its mirror is much smaller, so it doesn't see as faint as Rubin can. Its focus is precision astrometry. Rubin's is deep, wide, fast imaging. And ZTF, the Zwicky Transient Facility. It actually has an even wider field of view than Rubin, which is amazing. But its telescope aperture is much, much smaller, so it doesn't go nearly as deep. ZTF was really crucial as a pathfinder, especially for developing Rubin's alert system software. So Rubin kind of takes the best aspects, the width, the depth, the speed, and pushes them all to the extreme, all in one facility. That combination is what's truly new.
That really puts it in perspective. But this brings up, well, a relatively new challenge for ground-based astronomy, doesn't it? Looking ahead, we have Rubin ready to scan the skies, but there's this growing issue with satellite constellations.
Yes, this has become a major concern for astronomers worldwide. The issue is these large constellations of satellites, mostly for internet access, orbiting in low Earth orbit. When they pass through a telescope's field of view during a long exposure, they leave bright streaks across the image. Now, you can often model and subtract the streak itself, but the process leaves behind residual noise, and basically the pixels affected by the streak become scientifically useless. We saw this very clearly in images from the Cerro Tololo Inter-American Observatory, CTIO, right near Rubin, which has a similar wide field. Images just crisscross with Starlink trails.
And the sheer number of these satellites is just ballooning, isn't it?
It really is. Starlink alone has launched, what, over 7,000 already? With plans for 12,000, maybe even eventually over 30,000. And they're not the only ones. You've got Amazon's Project Kuiper, OneWeb, and potentially others planning similar mega constellations. Simulations specifically for Rubin's operations suggest that trying to actively dodge these satellites would mean spending more time slewing the telescope, moving between pointings. They calculated it could cost maybe 10% of the total available observing time just to cut the number of streaks in half. Even with, say, 30,000 satellites up there, predictions are that maybe 8% of Rubin's images could have at least one streak, which translates to losing something like 0.04% of the total science pixels.
Okay, so 0.04%. It doesn't sound like a catastrophic loss of data overall, but it's definitely an impact and inefficiency introduced.
Exactly. It's not ideal, and it complicates the data processing. It's also important to remember this primarily affects observations taken during twilight, morning, and evening, because later in the night, most of these low Earth orbit satellites pass into the Earth's shadow, so they're no longer illuminated by the sun and become invisible to the telescope. But yes, it's definitely a new environmental factor that astronomy has to contend with, and there's ongoing work and discussion with the satellite operators to try and mitigate the impact as much as possible.
It really is an incredible machine, the Vera Rubin Observatory. Just thinking about the journey, those huge, perfect mirrors, the giant camera, the sheer scale of the data, it's all designed for this single purpose, bringing us this unprecedented dynamic view of the entire cosmos.
Absolutely. Hopefully this deep dive has given you a really solid feel for why Rubin isn't just, another telescope. It's a genuine leap forward, a paradigm shift in our ability to observe the universe and tackle some of the biggest mysteries out there: dark matter, dark energy, the dynamic sky.
So the final thought to leave you with is this. Imagine what unknown unknowns are lurking in that absolute flood of data. What completely new kinds of stars, galaxies, or cosmic events will Rubin uncover that we haven't even dreamed of yet? How will its constant, relentless, wide-angle gaze fundamentally change how we perceive our universe, not as static, but as this vibrant, dynamic, constantly changing place?
Welcome to The Deep Dive, the show that, cuts through the noise and gets you straight to the heart of what you need to know. Today, we're peeling back the layers on a concept you've probably seen, 100 times, maybe even drawn it on a whiteboard somewhere: Maslow's hierarchy of needs. But here's where it gets really interesting, like right off the bat. That iconic pyramid, Abraham Maslow himself, he didn't actually create it.
That's right. It's kind of wild, isn't it? It's one of psychology's most enduring ideas, used everywhere: business training, healthcare. Yet the visual we all associate with it, it's not from the original source material at all.
Okay, so if we're going beyond just the pyramid shape, what's our mission today? What are we digging into? We're really going to explore Maslow's truly influential theory. Look at its history, how it developed, understand the nuanced meaning of each need, and then really get into the significant criticisms and cultural variations, things that often get overlooked. Our goal is basically to give you a comprehensive and hopefully intriguing shortcut to truly understanding this framework, offer some fresh perspective, maybe some practical insights for your own life. So let's unpack this.
Okay, sounds good. So to start, let's go back to the man himself, Abraham Maslow, an American psychologist. He first proposed this way of thinking about needs, about goals, what motivates human behavior, way back in his 1943 paper, A Theory of Human Motivation.
Right, 1943. And in that original version, he laid out 5 core sets of basic needs. Is that correct?
They did, yes. Those were physiological, safety, love, esteem, and then at the top, self-actualization. And he described them as being related to each other in what he called a hierarchy of prepotency.
Prepotency. Okay, what does that actually mean? Like strength, dominance.
Exactly. Strength or dominance. Physiological needs being the most fundamental, the most potent.
But how rigid is this hierarchy, really? I mean, are we truly stuck on one level until it's like 100% satisfied? Or did Maslow see it as more fluid?
That's a really crucial point he made. He specifically emphasized that a need doesn't require being 100% satisfied before the next one starts to emerge. Instead, he talked about it in terms of decreasing percentages of satisfaction as we go up the hierarchy of prepotency.
Okay, that makes so much more sense than some kind of rigid ladder. It sort of reframes how you might think about your own life, right? Like,
Yeah.
you don't need perfect financial security before you can even start thinking about relationships or something. It's more of a balance.
It absolutely is. And he also made this distinction between deficiency needs, he called them D needs, and growth needs. The bottom 4 layers, so physiological, safety, love, and esteem, those are the deficiency needs. When they're not met, well, that deprivation is what motivates us. We're driven to fulfill what we're missing.
Okay, but human brains are complex, right? We've got lots of motivations buzzing around at the same time. How did Maslow square that with this idea of a hierarchy, which kind of implies a strict order?
Yeah, he acknowledged that complexity. He knew we have parallel processes, multiple motivations happening simultaneously. His focus wasn't really on saying an individual focuses only on one need at any single moment. It was more about identifying the basic types of motivation and the typical order in which a certain need would tend to dominate the person. He was looking for the fundamental pattern.
Gotcha. Identifying the main driver at a given time.
Yeah.
And just to circle back to what we said at the start, it's worth saying again, right? While this whole framework is incredibly powerful, Maslow himself never actually drew that pyramid diagram we all know.
Nope. That visual came later, somebody else's interpretation. So given that sort of foundational understanding, maybe we should zoom in on each of these needs, start unpacking them layer by layer.
Yeah, let's do that. And we have to start at the very bottom, don't we? The physiological needs. I mean, we all get air, food, water.
Mm-hmm.
But what was the key idea for Maslow here, beyond just, basic survival?
It's really that relentless drive for what biologists call homeostasis, that internal balance. Think about it, if you're truly deprived of air, like everything else just fades away, that need completely dominates. So it covers air, water, food, warmth, clothes, shelter, sleep. Even reproduction falls into this basic category for him, the body's primary agenda.
Right. Makes sense. So once those immediate survival things are, fairly well taken care of, what's next? Safety. What does that encompass? Is it just physical danger?
It definitely extends beyond just physical safety, although that's part of it, protection from war, natural disasters, abuse, things like that. But safety needs also cover economic safety.
Ah, okay. So things like having a steady job, maybe some savings, insurance policies, that all fits under safety.
Exactly. It's about seeking stability in one's life.
It's funny, he wrote this back in 1943, but it feels incredibly relevant today, doesn't it? Especially with, the economy, job security worries. That search for basic stability is a big deal for many people.
It really is. And Maslow noted this level is particularly pronounced in children. They generally have a greater need to feel secure, and also individuals with disabilities. But adults are definitely impacted too, often around those economic concerns you mentioned, seeking that stability in one's life, as he put it.
Okay, so once we feel relatively safe, relatively stable, then the third level starts to emerge. Love and social needs.
Yes, exactly. This is where our interpersonal needs come in. That feeling of belonging, of acceptance within social groups. And these groups can be large, like clubs, maybe your coworkers, or small, like your family, intimate partners, close friends.
It's that fundamental human need to, love and be loved, both sexually and non-sexually, he said.
Right. And when this element is missing, people can become susceptible to loneliness, social anxiety, even clinical depression. There's even research showing how, say, financial stress can strain parent-child relationships, contributing to higher rates of depression in families. It all connects.
That definitely tracks. But I think I remember the sources mentioning a sort of interesting exception here, something that might even override these more basic needs sometimes.
They do mention that, yeah. In certain situations, things like peer pressure or even a powerful drive for creative fulfillment can actually supersede physiological or safety needs for some people. It just highlights again that the hierarchy isn't, totally rigid for every single person in every single moment. There's flexibility.
Okay, interesting. So moving up from belonging, we get to esteem needs.
Sure.
This one seems to have like two different sides to it.
It does, yeah. Maslow talked about a lower version and a higher version. The lower version is more about respect from others. So things like status, recognition, fame, reputation. And then the higher version is focused inward. It's about self-respect, feeling strong, competent, mastering things, having self-confidence, independence, freedom.
So it's not just about what others think of you, but crucially, how you see yourself.
Yeah.
And did Maslow see these as separate or connected?
He saw them as very connected. He emphasized they're interrelated rather than sharply separated.
Right.
And this level is just incredibly important, especially for children. Adults have a huge role here, providing opportunities for kids to discover that they are competent, that they are capable learners. It helps foster that strong sense of self.
Right, building that internal confidence. Okay, so that covers the original 5. But Maslow didn't stop there, did he? His thinking evolved and he started adding more layers later on.
Precisely. After esteem needs, he began to suggest including cognitive needs. This is about our craving for meaning, for information, wanting to understand things, curiosity. It drives what he called a will to learn and attain knowledge.
Ah, so that's like the intrinsic motivation for education, or even just enjoying activities that need, thinking and brainstorming, that basic human urge to understand.
That's exactly it. And then following cognitive needs, Maslow proposed aesthetic needs. This involves the desire to, beautify one's life, as he put it, appreciating beauty in the world around us.
So things like spending time in nature, maybe making your home environment pleasant, or even just expressing yourself through personal style. It's about connecting with beauty.
Yeah, appreciating and seeking out beauty and order. Even, like you said, organizing a messy drawer can provide a little bit of that aesthetic satisfaction.
Maybe. Okay, so after cognitive and aesthetic, we finally reach the big one, self-actualization.
Right. This is where we get that very famous quote from Maslow, "What a man can be, he must be."
Powerful quote. So what did he mean by self-actualization exactly?
He defined it as the realization of one's full potential, basically striving to become the most that one can be. He saw it as a kind of value-based system, an explicit motive. The earlier stages are sort of the step-by-step process towards this goal.
And examples could be anything, right? Like becoming the best parent you can be, achieving a major athletic goal, creating art, inventing something.
Exactly. It's unique to the individual. But then, even beyond self-actualization, Maslow later added one final, even higher level, transcendence needs.
Transcendence needs. Okay, what falls under that? Sometimes called spiritual needs.
Yes, also known as spiritual needs. He believed meeting this need produces feelings of integrity. It can raise consciousness to a higher plane of existence. Maslow felt that by transcending your own self, your own ego, you could look beyond your immediate culture, see other viewpoints more clearly. It's really about giving yourself to something beyond yourself, things like altruism, service, or spirituality. He equated it with the desire to reach the infinite.
Wow. So he wasn't necessarily talking about organized religion exclusively, but saw these spiritual values as having a kind of naturalistic meaning, something science could potentially study.
That was his view, yes, that they fall within the scope of an enlarged science. It really shows how his thinking deepened and expanded over time.
It really does. But, like any major theory, Maslow's hierarchy hasn't gone unchallenged, has it? There have been some significant criticisms and nuances pointed out over the years.
Absolutely. It's definitely faced its share of critiques.
One of the big ones seems to be about his research methodology, especially for understanding those self-actualized people. He famously studied figures like Albert Einstein, Eleanor Roosevelt.
Yes, that was quite controversial. His choice was deliberate. He wanted to study psychologically healthy individuals. He had this quote where he said, "Studying crippled, stunted, immature, and unhealthy specimens can yield only a cripple psychology."
Wow, strong words.
Very. But while that approach let him explore the peaks of human potential, it definitely raised questions about whether his findings could apply to everyone. Was it too narrow a sample?
Right. And then there's that whole discussion around the potential influence of the Blackfoot people on his theory.
That's quite a complex issue.
It is. So Maslow did do anthropological fieldwork with the Siksika Blackfoot Nation in Alberta, Canada, back in 1938. And there have been claims, particularly from some Indigenous scholars and elders, that he may have borrowed ideas from their worldview, their emphasis on community, selflessness, and spiritual connection, without giving proper credit when he developed his hierarchy.
But there are counter-arguments, too, suggesting maybe no direct borrowing. It sounds like there's disagreement.
There is. Some argue there's no direct evidence Maslow copied the Blackfoot model. However, a key point raised by Blackfoot scholars is that Maslow perhaps fundamentally misunderstood their philosophy. They emphasize a more circular, interconnected view of needs and existence, where community well-being is central, contrasting sharply with Maslow's linear, individualistic pyramid. They feel he didn't grasp that interconnectedness.
That difference in perspective, linear versus circular or interconnected, that seems crucial. And it leads into broader questions about the ranking and universality of the hierarchy itself.
Yeah.
Right, that's another major area of criticism.
Exactly. For instance, a review back in 1976 found, quote, little evidence for the specific ranking Maslow proposed, or even strong evidence for a definite hierarchy at all.
So the very structure, the ladder itself, was being questioned pretty early on, and then there was that criticism from Geert Hofstede in the 80s, calling it ethnocentric. What did he mean by that?
Hofstede argued that the hierarchy strongly reflects American individualistic values that focus on self-improvement and individual achievement at the top. He suggested it might not accurately represent motivations in more collectivist societies, where things like group harmony, acceptance, and community well-being might actually be prioritized over individual self-actualization.
Okay, that's a huge point. So if you're, say, managing a global team, you can't just assume this pyramid applies the same way everywhere. What motivates someone in Tokyo might be fundamentally different from someone in Toronto, even if the basic needs are universal.
Precisely. It forces us to challenge those one-size-fits-all models of motivation. And it extends to spirituality, too, criticisms around how individualism versus collectivism is handled there.
And what about the placement of specific needs? I think sex was mentioned as a point of contention.
Yes. Maslow placed sex primarily under physiological needs, alongside basics like breathing and food. Critics argue that really neglects the complex emotional, familial, and evolutionary aspects of sex and intimacy, though to be fair, Maslow himself did acknowledge later that sexual desire could also be linked to needs for love and belonging.
So it's not always clear-cut. And it sounds like more recent research, while generally validating that humans do have universal needs, still casts doubt on the exact hierarchy Maslow proposed.
That seems to be the trend, yes. The idea is that human behavior is probably driven by a more complex and unique set of motivations than a simple, fixed pyramid suggests.
Can you give us an example or two of that research?
Sure. There were studies comparing people in the U.S. and the Middle East, for instance. They found that during peacetime versus wartime, the importance people placed on different needs and how those needs grouped together actually changed. Or another study, this one conducted in Asia, found that community, which relates to Maslow's belongingness need, was actually rated as the highest order need by participants there.
Wow, community at the top. That really flips the pyramid. And didn't age also play a role in one study?
Yes, an older study from 1981 looked at different age groups. It suggested that the sequence of needing love and belonging versus needing self-esteem might actually be reversed depending on age. So maybe esteem needs become more important earlier for some, challenging the idea that Maslow's hierarchy is a strict developmental sequence everyone follows in the same order. It points towards needing a more nuanced view.
Definitely more nuance needed. And then, of course, there are critiques from different philosophical or religious perspectives, like the Islamic critique mentioned in the sources.
Right. That perspective emphasizes the centrality of spirituality right from the beginning, integrated throughout life, rather than seeing it as just the final stage like transcendence. It argues for a more balanced approach between material and spiritual needs in all situations, suggesting Maslow's hierarchy might oversimplify how these interact. It really highlights how profoundly our cultural and spiritual lenses shape how we even understand human motivation.
Wow. Okay, we've covered a lot of ground today. It's been a really fascinating journey, hasn't it? From Maslow's, revolutionary original ideas and really getting into the details of each need, to exploring his crucial later additions like cognitive, aesthetic, and transcendence needs, and then really importantly, grappling with all those compelling criticisms that push us towards a much more nuanced, more culturally aware understanding of what drives us.
It's true. And despite all the ongoing debates, all the challenges to its exact structure, Maslow's framework, well, it remains incredibly valuable, doesn't it? You still see it used widely across so many fields, business, education, therapy. It still offers a really powerful lens for trying to understand human drive, both in our personal lives and in professional settings.
Absolutely. So here's a final thought for you, our listener, to maybe chew on. Considering all these complexities we've talked about, the later needs, the cultural variations, the critiques, how might rethinking that traditional simple pyramid shape what you prioritize in your own life? Or maybe even change how you approach understanding the very diverse motivations of the people around you? If you had to draw it, what new illustration would you create for human needs today?